Now we'll see integral and differential form of Faraday's equation or Faraday's law. Faraday's law states that whenever there is a change in magnetic flux linked with the coil, an EMF is induced in the coil, and the magnitude of the induced EMF is directly proportional to rate of change of magnetic flux linked with the coil. So, according to Faraday's law, we have written the magnitude of the induced EMF is always equal to minus d psi by dt, where psi is the magnetic flux. Negative sign indicates that direction of the EMF is such that it opposes the flux change, opposes the change in flux. So, EMF induced is equal to minus d psi by dt. Now, to look at the integral and differential form of this equation 1, we have considered a conductor carrying current I. So, it has an electric field vector E in the direction of the current I. And we have considered a small elementary length or elementary current length of length dl. So, in terms of electric field vector E, the induced EMF E can be written as line integral of the vector field E in an elementary length dl. That I have taken as equation 2. Since whenever there is a current in a conductor, there will be a magnetic field associated with that in the form of a concentric circle in the direction perpendicular to the direction of the current, and if psi is the magnetic flux, then magnetic flux psi can be written as surface integral of the magnetic field vector B in an elementary surface ds. That I have taken as equation 3. Substituting 3 and 2 in equation 1, we get line integral of the electric field vector E is equal to minus d by dt of surface integral of the magnetic field vector B in an elementary surface ds. So, simplifying this equation, taking the integral symbol outside, surface integral of d by dt of magnetic field vector B. This is taken as equation 4, and this is the integral form of, that is, line integral of electric field vector E in an elementary length dl is equal to minus of surface integral of d by dt of magnetic field vector B in an elementary surface ds, that is taken as equation 4, is the integral form of the Faraday's law or integral form of the equation 1. In this equation, the left hand side of the equation represents the circulation of the electric field E around a closed path length L. Circulation of the electric field vector around a closed path length L, where L is the length of the current element. Right hand side of the equation, represents the rate of change of magnetic field vector B with respect to time through a closed surface of area S. It represents the rate of change of magnetic field vector B through a closed surface of surface area S. This is the integral form of the equation 1 or Faraday's law. Similarly, now let us look at the differential form of the equation. So, using Stokes' theorem, we have line integral of the vector field E is always equal to surface integral of the curl of the vector E, the same vector field E. So, this line integral of vector field, electric field vector E into dl can be expressed in terms of surface integral of the curl of the same vector. So, in the place of line integral of the vector field E, I have taken surface integral of curl of that vector and right hand side integral form of d by dt of B from equation 4. So, now both the sides we have left hand side, right hand side we have surface integrals. So, I have taken it into one side. Surface integral is taken common outside, that is curl of vector E plus dB by dt in an elementary surface area ds is equal to 0. This part is equal to 0. Our surface integral of ds should be equal to 0. But here surface integral of ds cannot be 0. Whenever there is a conductor carrying current with some finite surface area, the integral cannot be 0. Only the possibilities what is there in the bracket can be 0. So I have taken this as within the bracket, I have taken it outside. Surface integral of ds should be equal to 0. This is something like a into b is equal to 0. Here b cannot be 0. Only the possibility is a can be 0. So substituting a is equal to 0. Substituting a is equal to 0 will simplify the equation. So curl of E plus dB by dt is equal to 0. Curl of E is equal to minus dou B by dou t, or within the limits you can write it as dB by dt. This is the differential form of the Faraday's equation. The differential form of Faraday's law or equation 1. Here also the left hand side, it represents the curl of the vector E. That is left hand side we have curl of vector E that shows the tendency of the field lines to circulate around a given point. Tendency to circulate around a given point. Right hand side represents the rate of change in magnetic field vector B with respect to time t. And this is taken as equation 5, which is the differential form of Faraday's law.